Hi everybody, this video today is going to cover Newton's laws numbers 1 and 3. So starting off with Newton's first law. Before we actually get to that, let's talk about a couple of vocabulary terms: inertia, mass, and force. Inertia, we can say, is an object's resistance to changing its state of rest or state of motion. Mass is a quantitative measurement of inertia. So actually, inertia and mass are very, very closely related. They are essentially the same thing. It's just that mass is the number that you put to something's inertia. A force is a push or a pull on an object, and the SI unit of force is the Newton, and a Newton is 1 kilogram meter per second squared. So this actually is quite convenient if you remember this. We will be talking about the size of a Newton. I have a little poster in the room that talks about how much is a Newton. A Newton essentially can be thought of as how much one apple, the weight of one apple, is a Newton. Okay, we've all heard of Newton's first law before. An object at rest, you know the rest of it, tends to stay at rest, and an object in motion tends to stay in motion. Now, this second part is actually quite important. And it's the part that we don't really say very frequently. Like, everyone kind of remembers that first part, but this second part is important too. It stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. And we've talked about that a little bit with the velocity in the x direction. Same thing. Velocity in the x direction is going to keep going in that x direction unless something stops it. And so this is the same thing. It's not going to slow down. It's not going to speed up unless something acts upon it. By an unbalanced force. Okay, well, what's an unbalanced force? Well, an unbalanced force is any force in any direction, but where it doesn't have something counterbalancing it. So, you know, if you're pushing, let's see, you and your friend are both pushing against this exercise ball. I don't know why I thought of that. And you're pushing against it. Okay, if you and your friend are both pushing and it's not moving anywhere, it is a balanced force. But if you're pushing it without your friend, then it is an unbalanced force. Okay, so an unbalanced force is any force in any direction. And just like with you and your friend, if there's more force in one direction, then the object's going to move. Okay, in this unit, we do a lot of what are called free body diagrams. And so we're going to start talking about that a little bit. If we have a box placed on a table, are there any forces acting on the box? Okay, here's my table. I'm going to draw a box on top of my table. What are the forces that are acting here? Okay, well, hopefully we know that there are some forces. When we do this for our free body diagram, I'm going to put a dot. And I'm putting it right there where the box and the table hit each other, and I put it kind of in the middle of the box just to have some consistency here. Okay, hopefully you can think of some forces, and maybe you know, or maybe you don't, but one of the forces is the force of gravity. Now, however long that I draw that is representing negative 10 meters per second squared. And so if I draw another one in a different direction, if I want it to be a balanced force, in other words, is the box moving? No, the box is not moving. Then I want to draw my other vector the same way, because this box did not break through the table. The box is just sitting there. And so we have another force, and that force we call the normal force. F sub n is our normal force. And F sub g, of course, is the force of gravity. It's also the weight. You know how we talk about how astronauts weigh differently when they're on the moon than they do when they're here? Okay, that's because gravity is different. So the force of gravity is the weight. The mass stays consistent. The astronaut has the same amount of mass on Earth as he does on the moon, but his weight is different. And the weight, again, comes down from the center of gravity. And I just drew it right there where the box and the table meet each other. That's where we're going to draw our forces from. Okay, we have a new notation. It is this sigma. It's a Greek letter sigma. And that sigma, what it means is the sum of. So if you see sigma something, it means you're supposed to add stuff up. So over here, I have written down that if there is no change in motion, so this box is not moving. If there is no change in motion, then the sum of the forces is 0. So in this example, the sum of the forces, which is the force of gravity and the normal force, if we add those up together, then they would be equal to 0. Or if we wanted to move that one to the other side, we could subtract it over, and we would get the force of gravity is equal to the opposite of the normal force. And that makes sense because gravity is typically negative 10 meters per second squared, so that means the normal force must also be 10 meters per second squared. But this will be positive, this will be negative. Okay, what do you notice about these force vectors? We need to talk a little bit about those vectors, those arrows that we drew. There are some important things about them. And we already talked about this a little bit, but they are equal in magnitude. So the length of the arrow is equal to each other, but they're opposite in direction. And so again, if this is negative 10, this is positive 10. Does the presence of multiple forces on an object imply that the object must be in motion? Well, let's look at our example. We have multiple forces, more than one. Does that mean it's going to be moving? No, because the net force could still be 0, which it is in this case. If the net force is 0, then it's just sitting there. Okay, so I mentioned astronauts a second ago. Here's another question about space. In order for a space probe to travel to the end of the solar system, would it need to resupply fuel often? Why or why not? Well, let's think about that. If something is going to move, does it have to have a force on it? No, because things in motion tend to stay in motion. So you give it a push to get it started, like out of the atmosphere. And once it gets out of the atmosphere, there aren't very many forces acting against it. And so therefore, it's going to keep going. Things in motion tend to stay in motion. Now, in relation to the previous question, why do we have to continually refuel our vehicles on Earth in order to travel from one place to another? So why doesn't this concept work for us? Well, the reason is there's a force in the way. And what is that force? Well, you may not know it, but it's a force of friction. Friction is what allows your tires to have control. And if your tires don't have friction, then you are not going anywhere. And so that situation would be like if you're driving on ice. If you try to drive on ice and your tires don't have any friction, you're not going anywhere. So friction is what gives us control, but it's also what makes it so that we have to refuel. Okay, last question on this page. Does the motion or velocity imply that there must be a force present in the direction of the motion? Well, once again, let's think about that space probe in outer space. Does it have a force acting upon it? No. Things in motion tend to stay in motion. And so, therefore, it had a force to begin with. Something set it in motion. But once it got set in motion, it didn't need a whole lot of fuel after that. And so even if something is moving, that does not mean that there is a force acting upon it. Okay, let's turn the page. Okay, back to this concept of being on ice, a hockey puck. Draw a force diagram of a hockey puck moving along the ice. Show the directions of the velocity, acceleration, and force vectors. Okay, here's my ice. Here's my hockey puck. I need to show the direction of the velocity, acceleration, and force vectors. Okay, I'm just going to say that my puck is moving this way. So there's my velocity vector. Now, are there any forces acting upon it? Well, it's kind of a tricky question because you have to think about both the x direction and the y direction. There is a force of gravity, right? And if there's a force of gravity, is it falling through the ice? No, it's not falling through the ice. So there must be an equal and opposite force the other way. That's called the normal force. Now, is there any acceleration? No, there's not. It's just once it's hit, okay, someone hits the hockey puck, yes. But then once it gets hit, it is not speeding up, it is not slowing down, it is keeping the same exact velocity the entire time. What about forces? Well, all of the forces are balanced. The force of gravity and the normal force are balanced with each other. It's not floating up in the air and it's not crashing through the ice, so they are balanced. There is no force in the x direction. And if there is no force in the x direction, then there is no acceleration in the x direction. Force and acceleration go together. Force causes acceleration. If there is no force in the x direction, then there is no acceleration in the x direction. The only forces we have are in the y direction, and they are balanced. So according to Newton's first law, if an object speeds up or slows down, there is a net force acting on it. And so, and we just wrote this down, but I guess I jumped ahead of myself. If there is a net force, then there is acceleration. Acceleration and force go hand in hand. Okay, I mentioned that in this unit we're going to be doing a lot of free body diagrams, and so we need to talk a little bit about free body diagrams. Net force is you're basically looking at the force vectors and seeing, which ones kind of cancel each other out, basically. So forces are vector quantities, therefore to determine the net force acting in an object, free body diagrams will be used. Free body diagrams show all of the forces acting on the object, as well as the exact orientation, like up, down, left, right, or maybe at an angle, the magnitude of each force, and that's represented by the length. The length of the vector tells you how much it is, how big it is, how much, if it's a force, how much force it has. And then a designated coordinate system showing the positive and negative directions. Typically, when we talk about a coordinate system, we typically think as right and up are positive, left and down are negative, just like we would with a normal coordinate system. We can at times, and we will, twist this a little bit for our purposes. Okay, that is Newton's first law.